Okay, so here we are with valence shell electron pair repulsion theory. Now, some of you may have already watched the video by Tyler DeWitt on this. He does this much better than what I'm probably going to do in this video, but I'm just going to highlight a couple of points that we need to remember. We've also talked about this in class as well, so largely this will be somewhere where we can look in revision. You'll need to bear with me. My stylus has seemed to have broken tonight, so I won't be able to draw on the screen as much, but I'll see what I can do with my mouse. But basically, we're going to go through the basic shapes you need to know and look at how we describe those. There are a number of ones beyond what we do in the standard level course. Okay, so if you're looking at things and reading things and you see a whole bunch of other shapes like T-shape and seesaw, don't worry, we'll get to those when we do higher level. But for now, there's just a few that we need to know and become familiar with. So, as we talked about, VSEPR theory or valence shell electron pair repulsion theory is the main theory that dictates how the shape of molecules comes about. It was originally developed back in 1940, so it seems like a long time ago, but really it was in the 20th century. And it was done by a couple of people at Oxford University and also in University College London. They refined it back in 1957. So that's just a bit of history for you. It's been around for a while, but not that long if you think about it. Essentially what this theory is it states that electron pairs will move so that they orientate themselves as far apart as possible when a molecule forms. Okay, now again, this is an idea of a model in science, so relating this back to our ideas that we look at in talk and our nature of science. This isn't something that we have a picture of, it's something that fits the best observation data that we have, and we can measure things like bond angles when we get X-ray crystal structures and things like that. So again, it is a model, but it fits most of the data pretty well. Okay, so again, it comes back to pairs of electrons, remembering that electrons like to be paired, that one up, one down spin, okay, and that particularly we're looking at the ones in the outer shell, so they're going to stay as far apart as possible, because remember, they're all negatively charged, so they're going to repel each other, so they're going to want to keep away. So this basically states shape depends on the number of bonding pairs and the number of non-bonding pairs. So when we're talking about bonding pairs, we're talking about the pairs that are shared, okay, between the atoms. And then the non-bonding pairs are those ones when we draw our Lewis structures that are paired up already and don't participate in a bond, okay? So they're just those pairs of electrons that are sitting there around the central atom, okay? The bond angle is the angle between the central this one here, where we look at this angle here between the two hydrogens on water here. So it's the angle formed when we look at going from the hydrogen through the oxygen and out to the other hydrogen. So this angle here is what we refer to as the bond angle. Okay, and we'll look at the impact of non-bonding pairs on those. Okay, we don't consider them as part of the shape, but they certainly dictate how our shape will form. Really important when explaining any questions when the question asks you to explain in terms of VSEPR theory is that while they all try and get as far away as possible, they have different levels of repulsion. So our non-bonding pair and non-bonding pair repulsion is greater than our non-bonding pair to bonding pair repulsion and greater than our bonding pair to bonding pair repulsion. And you can get away with actually specifying this in an exam as like NBP to NBP using the greater than sign, and then NBP and BP, and then BP and BP, because it can take a while to write all of that out. So first shape that we need to do is linear, and this is anywhere where we have one bonding pair of electrons. Okay, so, and we've talked about how in that linear bond, we have free rotation around here. Just the point, you can represent your non-bonding pairs as lines. I recommend that you do them as dots instead. It just makes your diagrams a bit clearer and helps you to predict the shape a bit easier. Okay, so examples of this include HCl, hydrochloric acid, hydrofluoric acid, hydrobromic acid, our dihydrogen difluoride, and our chlorine gas, anywhere where we've got that single bond between two atoms. Okay, and we can look at carbon dioxide, but we'll add a little bit more to carbon dioxide a little bit later on. So, and this is where we start to look at those. So carbon dioxide would come under this one, this linear planar idea, where we have multiple bonds, not just a single bond in here, and that restricts the rotation. But if you call all or either of these linear, you'll still get the marks in the exam. It's just good when we move on in our ideas of chemistry to realize that these planar molecules don't have that free rotation. And we see that when we have double or triple covalent bonds. Tetrahedral. So we've seen tetrahedral a lot. A lot of you are familiar with drawing it from year 10, but don't exactly understand why. But our tetrahedral is where we have 4 bonding pairs, okay? Remembering that carbon can make 4 bonds. So if it's making these 4 bonds, they will all be kind of equal. And that means that they'll distribute evenly around that central atom, remembering that we live in 3 dimensions, not 2. So instead of being at 90 degrees, they actually spread out in a sphere around that central atom, which gives us a bond angle of 109.5. Okay, so that gives us more space because 109.5 is more than 90, and they're actually now managing to be further apart than what they were before. Okay, so again, we see things like this. We can have CH4. We can change each of those hydrogens out for a chlorine and get CCl4 or CF4. And we can even have CCl2F2. We can have different combinations. But anytime carbon has 4 bonds, we're going to be talking a tetrahedral arrangement. Trigonal pyramidal, and one of my favorite pictures here, okay, which shows that that lone pair occupies more space, okay, and this is why it pushes things around, okay. This lone pair repulsion that we have up here is pushing the hydrogen atoms down because the repulsion up here is greater, pushing these hydrogens down so that it has more space. Okay, so this is a trigonal pyramidal, okay, meaning that we have a triangle-based pyramid, okay, and we see this every time we have 3 bonding pairs and a lone pair on the central atom. The lone pair sits up on top, and then the 3 things that are bonded to the central atom get pushed down in a little bit of a pyramid shape. Okay, and we'll see this with anything that bonds to nitrogen, because nitrogen likes to form 3 bonds and has a lone pair on top. And then phosphorus, which has the same valence shell configuration as nitrogen, will form the same type of shape as well. Okay, so things that are in the same group tend to form the same kind of shapes, and that's a bit of a hint for you when looking at your periodic table. Okay, V-shaped or bent, 2 bonding pairs and 2 lone pairs. We see this in SO2 molecules, H2S molecules, and our most characteristic time we see this is our water molecule. So these 2 big lone pairs up here pushing these 2 hydrogens together so that we get that bent shape rather than a linear shape. So these are pretty much the ones that you need to know for standard level. We need to know our linear shape with 180 degrees. We need to know our bent shape, which will have less than 120 degrees. And we need to know our ammonia trigonal pyramidal shape, which again is less than 107. Okay, and you'll notice this guy over here, and if you remember from the last video in our exceptions to the octet rule, okay, we will see here, this is boron, and remembering that boron is an exception, it's happy with 6 valence shell electrons. So when it forms, it has 3 bonds, and we get this trigonal planar where it's actually 120 degrees. I wonder if you can come up with some different molecules that may also follow that shape. You might have to look at some that maybe have a double bonded oxygen in them. Okay, so going to that double bonded oxygen idea, okay, we can start looking at these bonds as being a negative charge center, or a better term for that is actually an electron domain. Okay, so we tend to look at this as a negative charge center between our bonds, and then we can count those up. Okay, so this one here would have 3 electron domains. Okay, 1, 2, 3, even though it has 4 bonds. Okay, because we've got this double bond, but we count that as 1. Okay, we count them as a single charge center. But these single charge centers actually push these hydrogens down a little bit more. There's a bit more electron density, a little bit more repulsion. So instead of being 120 in all areas, we get this one being a little bit closer at 116 and these ones being a little bit bigger. Okay, just because the electron pairs on here and this double bond are pushing them closer together. So it changes our bond angle. So these are the ones you need to know, okay, and an approximation of their bond angles, trigonal planar, okay, and bent, remembering that bent will be less than 120, okay, and water in particular is much less than that, okay, and then our tetrahedral and our trigonal pyramidal, okay. So these are the ones we need to know for SL, and yes, you do have to know the bond angles. So these ones are for you to have a try. There's some pretty tricky ones here and some that will lead us into discussions about our next video, which is going to be on resonance structures and how things can move about within an atom. So before we finish up, I would like you to have a go at these and we will go through the solutions in class. Okay, so good luck. Hopefully VSEPR is making a bit more sense now, and then we will move on after we've done some modelling in class. See you then.